use decimal expansion. There is no problem in having this number non-terminating. Alright, this is just for the sake of precisions that we have here. Alright, now let's see whether we can convert back this decimal number back again to rational numbers or back again into fractions. Let's see what we can do with this. Alright. So as you can see, we have got our fraction number over here. That is 375 by 1000. That is, if I try to reduce it down to a point where I cannot reduce it even further, that is 3 by 8, I get one number is odd and another number is even number, and the common factor between these two is 1. So that means I've reached a point where I cannot reduce it down. And as you got to know that every rational number or every fraction of the rational number cannot be reduced even further. Alright, so we've got decimal number for this 3 by 8, that is 0.375. Alright, let's take 3 by 10. Obviously we know that 0.3. Now we will see the example for whether we can convert back the decimal number back to the fraction. Let's see over here. We have got the example over here. That is, we have, let's say we have x is equal to 3.33. This is a decimal number we have to work on, and we want to convert this decimal number back again into fraction number or a rational number, right? A rational number means the numerator and the denominator should belong to integers, and they are at the least form. They cannot be reducible even further. Now it is a procedure as to get this fraction. So what we have, the number here, the 10th position of a number, the decimal number over here is repeating, right? So we are multiplying it with 10 on both sides. I got 10x is equal to is equal to 33 point something like this. Now I'm subtracting this 2, I'm getting this 9x is equal to 30.000, and then if I send this 9 to other side, I get x is equal to 30 by 9. Reducing down, I get 10 by 3, which is our rational number, which is irreducible. Alright. Now there is another method for converting the decimal number back again to rational number. That is, we can use geometric progressions, but for now this is not we are going to discuss, but it is also another procedure to get our job done. Now, if you might have observed that whatever we are doing, whenever we are converting a fraction or a rational number into decimal expansion, I'm getting these two type of decimal expansions. That is, we've got terminating number. Alright, as you can see, 3 by 10, that is the decimal expansion of 3 by 10 is equal to 0.3, and it is terminating. Here we also have 0.375. In this case, we also are getting terminating decimal number, but what about the case that is we have here 10 by 3, you're getting non-terminating recurring number. So if you take any number, any rational number from the number line, if you pick it and try to find out the decimal expansion of that, you would get either of these format. You would get either of these decimal expansions. That is, one is terminating, another one is non-terminating. All right. So, do we have any anything that we can have in the number line, or we are leaving, or could have any another type of number that the number line doesn't consist, or maybe it consists but we cannot have in this form? Let's see in this next concept that we have here is, let's, for the sake of argument, there could be a possibility of a number which cannot be in the form of a rational number, or as well as or as well as it cannot be in the form of two types of number, two types of decimal expansion. It should not be either these form, or it should not be of the fraction form. So let's say we can have type 3, that is 3.1416, or to be precise, I'm getting 3.145, and I'm getting indefinitely a large number which is never ending, and it is not repeating, not reoccurring, and it is neither terminating. So it is type 3, which is different than these two types that we have here, that is terminating and non-terminating recurring. We are getting another type, that is maybe there could be a chance of having this type of numbers, that is non-terminating, but non-terminating and as well as non-recurring. So we are just taking a chance over here. Now let's see whether this type of number really exists in reality or not. We will see that. All right. So Pythagoras theorem, or Pythagoreans say that if we take an isosceles triangle, right triangle, with the sides equal to 1 and 1, as it is isosceles, the two sides should be equal, right? And they say that these two sides, the square of these two sides, when added up, they will give the square of the hypotenuse. We have the proof for that as well. By taking the area of the square of this side, by drawing another square over this side, and another square this side, and another square this side with this length. Okay, we don't want to go into that Pythagoras law over here, but we have a proof for that. But now, as you can see, we've got the proof that it says that c square is equal to the side square plus side square. But that's what I did over here. C square is equal to 1 plus 1. I got c square is equal to 2. That is c is equal to root 2. That the number is equal to root 2. A new number that we have not discussed yet in the previous number line. Maybe it should be there somewhere at the number line, but we don't know yet. Maybe this number root 2 does not belong to number line. Don't know what is the case, but it has a length, right? So our common sense logic says that it has length. It can be present on a number line, right? Another example that we have here, if we take an A4 size paper, and by similarity law that we have, if the side of the square rectangle, that is, for example, I've taken over here ax, and the breadth it is equal to x. The length is 8 times bigger than the breadth, and now I've got the ax as a length and the x as a breadth of a bigger rectangle over here. Now I'm dividing this rectangle in two parts from the middle. Then I'm getting another rectangle with the side, this side equal to ax by 2. We have got the another side equal to x. The similarity law says that the ratio of the sides of two shapes will be similar or same. So we have got length of a larger rectangle divided by the breadth of a larger rectangle will be equal to the length of the smaller rectangle divided by the breadth of the smaller rectangle. Now if you solve this thing up, you're gonna get a is equal to root 2. Again, we got the root 2 over here. What could be root over here? I don't know. So we will see again. We will see another example. Okay. We have got the circle over here. The perimeter of the circle, or we can call it as circumference, and we have got the diameter of that circle. All right. So again, if you divide the ratio of circumference and then the diameter of a circle of a small circle, you could get 3.1. If you have bigger circle with the bigger diameter, bigger circumference, you get more precision over measurement. You get 3.14. If you keep on doing that, at the end you might get something more precise and never ending. That is, again, we've got some number that uh, doesn't belong to rational numbers. We've got two type of numbers here. That is, numbers which looks like root 2 and the number look like this. So maybe they have some common similarity between these two. And as you can see over here, right over here, this example is for the this example right over here, which is never ending. It is the example for the precision over finding the ratio between circumference and the diameter. Okay, let's for the sake of argument, can we convert these type of numbers, these type of root numbers, back again into fractions? Can we do that? Okay, in order to do that, all right, in order to convert decimal numbers back again to rational numbers, we have three methods, right? So if the numbers are getting repeated, all right, if the numbers are getting repeated, as you can see, if the numbers are getting repeated, we can do some calculations over here, and we have came across this fraction. But if the numbers are not repeating and they are going to indefinite times, and still we have another method, that is by using geometric progression. Geometric progression deals with a common ratio that is fixed, but in the case of root 2 or another number that we have seen here, that is pi, in the case of these two numbers, they don't increase with a fixed ratio. They have some different ratios going on. So we cannot convert these numbers back into rational numbers. Right? Alright. So we will see whether root 2 belong to number line or not. For that, take a number line over here. We got a number line over here. The side of a triangle here is equal to 1, and this side is as well as equal to 1. So we've got both sides equal to 1 by Pythagoras theorem, as we have seen it earlier, that by Pythagoras theorem we are getting this equal to root 2. Alright, now take a compass, measure this line and try to draw it over here. Now as you can see, it is bit lesser than 1.5. It is somewhere between, it is somewhere before 1.5. Alright, so that means root 2 belongs to number line, but it is not a rational number. So what do we call this? So we will name this type of number opposite of rational number, or we can more accurately we can say them, these type of numbers, irrational numbers. Means the numbers which cannot be represented in the form of p by q. They can be represented on a number line, but they cannot be represented as a fraction of two integers. It is not possible. Let's see if you are getting confused, what is root over here? What do we call this root, and where this root came from, and what is the use of this root? Whether this root exists in real life applications or not, whether this root to a number or it is not. So for that, we have another example that we have here is, so we were actually looking for what is root. We were actually looking what is this root number, where does this root came from. So we have a square with the side that is equal to 5 and 5. The area of the square is equal to 5 into 5, that is equal to 5 square, that is equal to 25. We got 5 square is equal to 25. Now we know that if it's on this plus to the other side, I'm getting something which is opposite to that, right? Plus is opposite to the negative, negative is opposite to the plus, multiplication is opposite to the division, and same goes with this one as well. Now if I send this to other side, I should get something which is opposite to that. That is, I think I would get 2. When we send to the other side, it will become a power which is half of this. Alright, that is pi is equal to root 225, that is equal to pi is equal to 5, means we are getting this root, that is equal to 1 by 2 power. Alright, and root basically means that it helps us to find exactly two similar numbers, same numbers, which when multiplied with themselves, they get some other number. In this case, we have 25. It is a perfect square number. Perfect. This is perfect square. Perfect square means this number is getting multiplied 2 times, and we are considering it as a perfect square. So root 25 is a perfect square root number. That is, it gives when we multiply this 5 again and again. So we can have indefinitely or infinitely many numbers if we add. Alright, if we add, we can have infinitely many numbers, and they doesn't belong to integer, and they are also not rational numbers. There are some different numbers. We say that these type of numbers we are considering as opposite to rationals. We are naming it as irrational. Alright, we have rational numbers. As we all already know about rational numbers, the rational numbers are the fractions which can be reducible at some point where we cannot reduce even further, as we have seen back then. So these are the rational numbers, right? Just for the review. Now we have another concept, that is, we are dividing the sequence of numbers, that is, we are dividing the number line into 2 different types, that is, even numbers, and then we have odd numbers. Even numbers are the numbers which are divisible by 2, or we can say that the numbers which have the factor 2, odd numbers which does not have the factor 2 in their prime factorization. For example, I've got the sequence of numbers over here. All the numbers here belong to integers, right? Now each and every number can be written as, or can be expressed as, the product of some other numbers, right? We have seen that each and every integers can be written as a fraction of 2 numbers. Now in this case, we can represent each and every number sequence into product of 2 numbers. That is, 2 can be written as 1 by 1 into 2, 3 can be written as 1, 3, 1 into 2. So as you can see, we have 4 equal to 2 into 2, 5 equal to 1 into 5, 6 into 2 into 3. We have expressed all the integer in the form of these prime factors. I'm not using any other number here except prime numbers. Prime numbers are those kind of number which are divisible by itself and 1. Alright, so as you can see, we are getting numbers alternate even number. That is, this number is even, and then we have this number is even, then we have 6 is even, then we have 8 is even. The rest of numbers which are not even, we are considering them as odd number because they don't have the factor 2. They don't have the 2 in their prime factorization. We have 3, that is 3 here, we don't have 2 over here. We don't have 2 over here. Here in this case we have 2, we have 3. Alright, so this is even, right? We don't have 2 over here. You can do to all the integer. You won't get you will get all the numbers